If you could step far outside our galaxy and watch from some impossible vantage, you would see no glowing cities of stars. You would see, instead, a ghostly lattice. Veins of something unseen thread the void, joining islands of light like bridges of shadow. This scaffolding is not made of stars, gas, or planets. It is made of darkness. We call it dark matter. We do not know what it is. We only know it is there because it pulls. Every star in a galaxy revolves as though glued to an invisible wheel. Astronomers once expected the outermost suns to travel slowly, dragged by the mass we can see. They do not. They hurry along, faster than gravity from visible matter allows, as if the rim of the galaxy rests inside a deeper well whose walls we cannot perceive. The same hidden presence steadies whole clusters of galaxies so they do not drift apart. Without this dim cocoon, the luminous swirls we photograph through our telescopes would have flung themselves to pieces eons ago. Imagine the sun as a single mote of dust in a cathedral at midnight. The nave is vast, echoing, almost empty. Yet something thick and heavy moves between the pillars, bending the air, shaping silence. That something outweighs the dust by a factor of nearly 6 to 1. Across the cosmos, the same ratio repeats. For every pound of stars, of gas, of planets, of us, there are 5 pounds of something that never shines. We first suspected its existence in the 1930s, when Fritz Zwicky weighed the Coma cluster and found it obese. The galaxies within the cluster scurried so quickly that their combined visible mass could not hold them. Something else, something massive, must glue the swarm together. Zwicky called the missing heft dark matter, a phrase both blunt and honest. It is matter, and it is dark in the most complete sense. It emits no light, absorbs no light, reflects no light. Light passes through it as though through perfect glass. 70 years later, the Hubble Space Telescope stared long enough at a tiny patch of sky to record a picture known as the ultra-deep field. Behind every galaxy in that portrait, astronomers noticed distortions. The shapes of distant islands of light were bent, like faces glimpsed in warped mirrors. Mass bends space, and space bends light. By measuring how each image was twisted, we mapped the invisible mass lying between us and the far horizon. Again, the maps revealed a web, filaments, knots, great voids. Dark matter has drawn the universe into a foam of tendrils hundreds of millions of light years long. Curiously, it does not seem to swirl or spiral. Where galaxies collide, dark matter appears to sail through the carnage untouched, while clouds of gas collide, slow, and glow. In the Bullet Cluster, 2 groups of galaxies pass through each other like ghostly ships. Optical images show starlight. X-ray images show hot gas stripped and left behind. Gravitational lensing shows the mass continuing on its way, unimpeded. Dark matter does not interact with ordinary matter except through gravity. It is socially aloof on the cosmic stage, yet indispensable to the choreography. What could this stuff be? The inventory of possibilities is short, strange, and humbling. Perhaps it is a swarm of ancient particles born in the first instant after the Big Bang. They would be heavy, slow, and dark, weakly interacting massive particles, WIMPs for short. Or perhaps it is even lighter and faster, a population of neutrino-like phantoms called axions, billions of times less massive than electrons. Or it might be primordial black holes, small pockets of gravity forged from extreme density, wandering the void like mute cannonballs. Each hypothesis leaves footprints. If WIMPs fill the galaxy, Earth must plow through them like a ship through fog. Once in a rare while, one should strike an atomic nucleus and deliver a minuscule kick. Deep underground, where cosmic rays cannot reach, laboratories wait in darkness. Crystals of xenon or germanium rest at nearly absolute zero, listening for the gentle tap of a particle that has never been seen. So far, the taps are ambiguous whispers. Decades of patience have shrunk the hiding space, but the creature itself remains at large. Other hunters take a different tack. In the vacuum of space, two spacecraft set silver sails and listened for the faint pressure of dark matter passing through. They heard the constant patter of dust, the sigh of solar wind, but no unmistakable sign of the missing mass. Particle accelerators attempt to summon dark matter into existence by colliding protons at nearly light speed. If energy disappears in a detector, it might herald the birth of something that refuses to interact again. To date, the account books stubbornly balance. Meanwhile, astronomers watch the infant universe. The cosmic microwave background is a fossil glow released when the cosmos was 380,000 years old. Slight hot and cold spots speckle that glow. Their sizes tell us how much gravity was present to compress the primordial gas. From those speckles, we infer the cosmic recipe: 5% ordinary matter, 27% dark matter, 68% dark energy. Dark matter was the seed around which galaxies could later bloom. Without it, the universe would be a smooth, sterile sea of hydrogen and helium. With it, the gas cooled, clumped, collapsed, and ignited into the first stars. Consider the implications. Every galaxy you see, every star that warms a planet, every world that might hold oceans or forests, exists because something invisible tugged gently on atoms. We owe our existence to a substance we have never touched, yet we still do not know what it is. We name it, map it, weigh it, but we have not held a single particle in our hands. Dark matter remains a word for ignorance wrapped in mathematics. In some quiet moments, astronomers admit a stranger possibility. Perhaps our understanding of gravity itself is the mirage. Perhaps on the vastest scales, gravity behaves differently, and dark matter is the phantom we invented to balance an erroneous equation. This idea, modified Newtonian dynamics, tweaks the laws of motion so that no extra mass is required. It explains some observations neatly but fails on others, particularly on the subtle ripples in the cosmic microwave background. Most minds remain unconvinced. The majority still expect that one day a particle, a track, a resonance will announce the unseen. Until then, we live inside a cathedral whose pillars we cannot see. We navigate by the echo of their gravity. We chart them through the bending of light, the motion of stars, the slow dance of clusters 1,000 galaxies strong. Every time you look at the Milky Way, you witness a pale river of stars suspended in a much vaster ocean of darkness. The stars are the froth, the ocean is the substance. There is a strange comfort in this. So much of human life is built upon what remains hidden. The lattice of atoms inside a table, the currents of air that carry a bird, the slow drift of continents beneath our feet. Dark matter simply extends the pattern outward into the cosmic night. It tells us that visibility is not a prerequisite for importance. The universe is held together by what we cannot see, and the search continues. New detectors grow larger, colder, quieter. New telescopes will map the sky in richer detail, tracing how the cosmic web has thickened over 13 billion years. Perhaps a flash in a mine shaft will one day coincide with a burst of neutrinos from the sun, and physicists will finally nod, convinced that the darkness has spoken. Or perhaps the answer will arrive in a form we have not yet imagined, carried on instruments not yet designed, interpreted by minds not yet born. For now, we float within the invisible architecture, tiny luminous motes caught in a web whose threads we sense only by their tug. We are the dust that wonders about the darkness that holds it. And somewhere in the hush between heartbeats, the darkness continues to gather, to pull, to shape the luminous dreams we call galaxies. In the hush between heartbeats, the cosmos sometimes speaks in a single, searing syllable. A radio whisper, thinner than a flute note, races across oceans of intergalactic night, climbs our antennae, and is gone before a lightning bug can blink. We call it a fast radio burst, an FRB, and it is as strange as any lighthouse that flashes once, then never again, while the shore it guards remains invisible. The first came in 2007, hidden inside an old data tape recorded 6 years earlier at Parkes Observatory in the Australian outback. A graduate student, hunting for the rhythmic pings of pulsars, noticed a burst so bright it saturated the receiver. 5 milliseconds long, it carried more energy than the sun emits in a month. Yet no telescope saw a flare, no eye perceived a spark. It was a shout printed on silence, and for years no one believed it. Too many microwave ovens, too many earthly pranks had cried wolf from the same site. But the pulse had traveled too far, had dispersed too perfectly for terrestrial mischief. Something real had screamed across the universe, and we had only just begun to listen. Since that quiet revelation, the sky has proved restless. Hundreds more have arrived, some from the gentlest backwaters of the cosmic web, others from galaxies so star-battered they seem bruised by time. They arrive without etiquette, no greeting card, no return address beyond a smear of radio waves stretched by the sparse fog between galaxies. Each flash is a courier carrying news of an engine we have never seen. News so compressed that its envelope is measured in microseconds. Yet its message speaks of energies that dwarf our sun's lifetime output. If you could bottle a single FRB, you could power human civilization from now until the last star burns out. But the bottle melts before you can grasp it. Distance lends them grandeur. The farther we look, the louder they seem, as though the universe itself were cupping its hands around a secret. Some have crossed 8 billion years to reach us, light that began its journey before Earth had cooled enough to crust. When that burst started out, our planet was still molten ruby, and no continent had risen to break the planetary ocean. The burst arrived only yesterday, measured by the clocks of stars, yet it brought with it the metallic taste of deep time, a reminder that the cosmos is older than any biography written in stone or bone. Astronomers now sort these arrivals like forensic linguists parsing an extinct tongue. Some bursts speak once and fall mute, a solitary syllable echoing down the epochs. Others repeat irregularly, stubbornly, as if something broken were trying to remember a forgotten word. The repeaters stutter, sometimes waiting days, sometimes months, then unleash a dozen bursts in an hour, each with its own fingerprint of frequency and brightness. Between the two populations lies a divide we cannot yet cross. Are they cousins, or are they entirely different species? Theories bloom like night flowers, each luminous for a season. Perhaps the progenitor is a neutron star, city-sized, heavier than our sun, spinning so fast that mountains a centimeter tall become 1,000-kilometer blades, carving the vacuum and flinging radio light into the dark. Or maybe two such stars spiral together, their magnetic fields braiding until they snap, releasing a snap of energy that rings the fabric of spacetime like a drum. Another voice suggests a magnetar, a neutron star armed with the strongest magnetic fields known, fields so intense they can ring photons from the empty vacuum itself. When its crust cracks, starquakes ripple through a magnetic lattice more powerful than any forge, and for an instant the star becomes a beacon visible across the observable universe. Yet none of these explanations wears the garment of certainty. Each fits parts of the evidence, none fits all. Some wonder if the bursts are not natural at all but beacons, intentional or collateral from technologies we have not yet imagined. A civilization harvesting energy from the black hole at its galactic core might leak radio light as we leak the glow of cities into orbital night. But the thought remains speculation, fragrant yet unproven, a ghost haunting the corridors of data. Between the bursts, astronomers wait in the hush of control rooms lit only by monitor glow. They have learned patience. When the next flash arrives, it must be caught in the act, its dispersion measured, its sky position narrowed to a hair's breadth smaller than the apparent width of a coin held at arm's length against the moon. Only then can larger telescopes swivel, hunting for a fading afterglow in visible light or X-ray, a dying ember that might whisper what the radio scream could not. Most searches return empty, yet the few successes stitch a sparse constellation of clues. One repeater sits inside a dwarf galaxy busy with new stars, a place where stellar furnaces burn bright and die young, a nursery of cataclysms. Another solitary burst traced to a massive spiral, its origin offset from the galactic center, far from the maelstrom of any supermassive black hole. The diversity mocks every neat taxonomy we devise. Energy scales humble the imagination. A single millisecond of an FRB can outshine the combined radio output of every galaxy in our local cluster, including the Great Andromeda and her trillion suns. Yet the same burst, if converted to visible light, would appear to the eye as a star no brighter than the faintest scene from a dark countryside. The cosmos is not obligated to make itself obvious. Repeating bursts gift us a tool. By watching their dispersion shift, we can map the wandering wisps of ionized hydrogen between galaxies, invisible threads that trace where the universe has gathered its breath. In this way, FRBs become flash lamps in a cavern we could formerly only grope through. They illuminate the cosmic web, the scaffolding upon which galaxies hang like dew along a spider's silk. Tomorrow's catalogs of ordinary matter may owe their completeness to these extraordinary sparks. Future observatories are being built not on remote peaks, but in software, vast arrays of antennas that stare at the sky with compound eyes. In the next decade, thousands of bursts may be caught daily, their positions refined until we can match them to individual neighborhoods within distant galaxies. When that census arrives, we may finally see the pattern. Do they cluster where stars collide, where magnetars are born, or where civilizations might gather the energy of suns? Or will the map simply deepen the mystery, revealing new questions we have not yet learned to ask? For now, we live in the afterglow of ignorance, a state that science finds strangely fertile. Each burst is a reminder that the universe is still wild, still capable of surprise. They arrive, speak, and vanish, like nightjars calling once from a forest we have not entered, leaving us to wonder whether the next footstep will disturb silence or revelation. Perhaps the greatest gift of these cosmic whispers is humility. They arrive from places we will never touch, yet they touch us, altering the chemistry of curiosity within our minds. They remind us that listening is a form of travel, that attention can cross gulfs no vessel will ever bridge. Long after our instruments have cooled and the last data drives spin down, the sky will still speak in languages we have not invented, and the night will still belong to questions rather than answers. Somewhere in a galaxy whose light is only now beginning its journey, another brief flare ignites. It is already on its way, threading the dark between clusters, slipping past orphaned stars and planets not yet formed. It will reach us in 50 million years, a blink in cosmic time, but long after our names have turned to weathered stone. Still, if someone is here to listen, the burst will arrive like a letter addressed to occupancy, a reminder that the conversation is never truly over, only waiting for the next breath, the next question, the next pause in which the universe leans close and whispers something we have not yet understood. Ripples in spacetime gravitational waves from colliding neutron stars begin with silence. Not the silence of an empty room, but the silence of interstellar space, so complete that even thought seems to echo. In this quiet, two ghosts are circling. Each is a city-sized sphere packed with the mass of a sun, spinning 1,000 times every second. They have been waltzing for 11 billion years, drawing closer by a millimeter each century. No sound announces their approach. No flare betrays them. Only the fabric of reality itself remembers they are there. When at last they touch, the moment is brief. A shudder, no brighter than a spark on a dark ocean, runs outward at the speed of light. Space stretches, then relaxes, like silk pulled tight and released. The ripple is unimaginably faint. By the time it reaches Earth, the disturbance is smaller than the diameter of a proton laid across 10 light-years of void. Yet in two long, vacuum-straight tunnels in Louisiana and Washington state, laser beams quiver by that exact amount, and computers wake to the tremor. On that September morning in 2017, we felt the cosmos blink. What we call a gravitational wave is simply a change in distance between 2 points, a periodic breathing of geometry. You, too, breathe with every collision, but the motion is trillions of times smaller than anything your nerves could register. To notice it, we had to build an observatory that could measure the shift between mirrors hung on glass threads, shielded from the rumble of passing trucks, the heartbeat of the ground itself. Even so, the signal arrived first as a rising chirp, like a swallow's call speeded up 1,000-fold, then vanished into hiss. In that soft warble lived the portrait of 2 neutron stars dissolving into one. Neutron stars are what remain when a massive sun exhausts its fire and collapses. Imagine the Earth compressed until all its mountains, seas, and cities fit inside a teaspoon. A single thimble of this matter outweighs Everest. Gravity has crushed every empty space between atoms until electrons and protons themselves merge, forming a single ocean of neutrons. The star's surface is a crystalline iron crust a few centimeters thick. Beneath it flows a superfluid that ignores friction. Magnetic fields 1 trillion times stronger than the sun's reach out and tear empty space into sparks of pure energy. And yet, for all this ferocity, the star is stable. It will spin for eons, a bell struck once at the moment of birth, slowly losing tone. But stars are rarely born alone. Pairs drift through the galaxy, bound by the same gravity that will one day destroy them. As they spiral inward, they stir the vacuum, sending ahead faint warnings in the language of waves. Years before merger, radio telescopes can hear the pair as a ticking pulsar, each orbit shaving milliseconds off the beat. Then the tempo races. In the final second, the stars whirl hundreds of times per second, flinging out tendrils of superdense matter. Neutron-rich sheets peel away and collide, forging fresh nuclei in an instant. Gold, platinum, uranium, atoms too heavy for any ordinary star, condense in cooling clouds. A new sun flares, a kilonova, equal in brilliance to 1 billion ordinary suns, yet lasting only a few nights. For the first time, astronomers saw the flash with every sense open. Telescopes in the Andes recorded the color shift from violet to infrared, tracking how quickly the cloud expanded. Space observatories mapped the afterglow in X-rays, watching the fireball slam into surrounding gas. Radio dishes on 5 continents waited months until the expanding shell became transparent to longer waves. Meanwhile, the gravitational antennas continued to listen, measuring the pitch of the dying chirp to reveal the mass of the remnant. Too heavy to be a neutron star, too light to be a black hole, an enigma still. From these combined whispers, a new way of knowing the universe is emerging. We used to study the cosmos only with light, a single note on a vast keyboard. Now we listen with spacetime itself, adding a second sense. When the two agree, we gain confidence. When they diverge, mystery deepens. Already, the 2017 merger has tightened our estimate of how fast the universe expands, trimming the uncertainty that once allowed 2 rival camps to disagree by nearly 10%. It has shown that colliding neutron stars are the foundries where most of the gold in wedding rings was forged, ejected at 20% the speed of light to drift for ages before settling into new worlds. And it has hinted that the interiors of neutron stars may contain states of matter we have no words for, perhaps a soup of quarks no longer confined, perhaps something stranger still. There are questions left unanswered. Why do some mergers emit gamma ray bursts that punch straight through the cosmos, while others seem to cough quietly in darkness? What becomes of the remnant? Does it collapse immediately, or does it hover, spinning and radiating before vanishing behind its own horizon? How do neutron stars manage to keep their magnetic fields when their very surfaces crack under tidal forces? Each new detection adds another sentence to the story, yet the plot remains open. We are learning to read the ripples the way sailors once read swells, feeling for storms beyond the horizon. Where once we waited for chance sightings, we now schedule alerts. Robots swivel to stare at patches of sky the size of a full moon, searching for the first glimmer of a kilonova. Within minutes, amateur astronomers receive star maps on their phones, joining the chase. The universe has become an instrument played in real time, its chords struck by colliding phantoms. Still, the quiet returns. After the flash fades, after the lasers settle, after the last radio echo is logged, the galaxy resumes its slow turn. The remnant, whether star or black hole, glides onward, dragging spacetime behind it like a bridal train. Somewhere, another pair is winding downward, unaware of its fate. Their story will reach us in 100 million years, a telegram from the deep past. We will be here, our descendants or their machines, ears pressed to the fabric, listening for the next soft footstep on the drum of reality. Each ripple is a reminder that emptiness itself can be shaped, that distance can stretch and shrink like breath in lungs, that the heaviest things in existence are moved by the gentlest of nudges. In the hush between detections, we are left with the knowledge that the cosmos is not silent. It is only patient. Lift your eyes from the page for a moment and picture the Milky Way not as a frozen swirl but as a vessel adrift in a slow, majestic current. We are not stationary. Every star you know, every nebula you have seen photographed, every world we have named or imagined, glides through space at hundreds of kilometers each second. So quickly that, in the instant you finish this sentence, we will have traveled farther than the widest wingspan of our home planet. Yet the motion is not random. Something vast, something unseen, has arranged the flow. All the galaxies for hundreds of millions of light years move as though sliding down an invisible slope whose bottom lies hidden beyond the edge of the sky. Astronomers call that slope the Great Attractor. The name is modest for so grand a thing. It sounds like the title of a half-remembered legend rather than the designation of a physical structure. But modesty is fitting because we still do not know what it is. We know only its gravity. Gravity is the most democratic of forces. It cannot be hidden, only disguised. Wherever mass gathers, the fabric of spacetime bends, and light, traveling that bent terrain, betrays the presence of the bending. By measuring the deflection of light from distant galaxies, and by reading the temperature of hydrogen clouds as they drift, astronomers have mapped the velocities of thousands of galaxies. When the maps were first assembled, a pattern leapt out. Everything, including our local group, drifts toward a region in the constellation Centaurus, a zone obscured to optical telescopes by the thick stardust of our own galactic plane. We were being summoned toward something we could not directly see. Imagine a sailor on a moonless ocean who notices every compass needle tilting toward the same blank horizon. There is no flashing lighthouse, no rumble of breakers, only the silent, insistent tug. So it is with us. The Milky Way and its nearest neighbors sail at nearly 2 million kilometers an hour toward that blank place in the southern sky. 2 million kilometers an hour is 50 times Earth's orbital speed, yet the destination is so remote that we would need many billions of years to arrive. The journey itself is less strange than the fact that we can feel the pull at all. Gravity declines with distance, and the universe is expanding. Beyond a certain range, the cosmic expansion should outrun any local tug. The Great Attractor sits at the very boundary where gravity still wins the race, where matter has clumped so densely that it reigns in the expansion and turns it back into motion. To gather such strength, the hidden structure must outweigh our galaxy by tens of thousands of times. Ordinary matter, atoms, stars, gas, cannot account for the mass. Most of the pull comes from dark matter, that shy companion of luminous things. Dark matter does not glow, absorb, or reflect light. It announces itself only by bending space. Where it pools, galaxies gather like fireflies along an invisible stream. The Great Attractor appears to be the deepest such pool in our neighborhood, a gravitational well whose rim we happen to inhabit. Yet even dark matter may not be the whole story. Deeper surveys, sensitive to the subtle motions of dim, dwarf galaxies, suggest the pull is part of a still vaster edifice. Behind the Great Attractor lies something now nicknamed the Shapley concentration, a supercluster so huge that light needs 500 million years to cross it. Between that remote wall of galaxies and us lies a ridge of matter whose gravity combines with the attractors, turning a local drift into a river of galaxies hundreds of millions of light-years long. We are not merely falling. We are being herded. Mapping this motion is slow work. Our planet nests within a spiral arm thick with dust and crowded stars. When we look toward Centaurus, we peer through a fog of suns. Optical telescopes surrender, but radio ears still hear. The 21-centimeter whisper of neutral hydrogen passes unhindered through the murk. By timing that whisper, astronomers clock the speed of galaxies hidden behind the veil. Other surveys use the feeble glow of X-rays or the infrared warmth of dust to trace the mass. Each new instrument widens the view, and each widening reveals fresh currents. The universe, it seems, is less a still sea than a network of rivers, tributaries, and cataracts whose waters are galaxies themselves. Still, mystery accumulates faster than data. The Great Attractor's core lies roughly 150 million light-years away. At that remove, our maps grow hazy. Perhaps the mass is a single, gargantuan supercluster. Perhaps it is a knot in a filament stretching far beyond the horizon of the observable universe. Some calculations even hint that part of the tug originates from structures we will never see, regions whose light has not had time to reach us since the Big Bang. If so, the invisible hand guiding our galaxy belongs to realms forever outside our view. What would we find if we could travel there? Galaxies in dense clusters, blazing with the blue fire of new stars, their gas stripped into long comet tails by collisions. Radios of dark matter arching across the sky like cathedral vaults. Time itself would run slightly faster there, deeper in the gravitational well, so that a heartbeat near the attractor would outpace a heartbeat here by millennia across the age of the cosmos. Yet no one will ever take that voyage. The accelerating expansion of the universe drives distant regions away faster than any future craft could chase them. We are granted only the sensation of the tug, never the embrace. Pause and let that sink in. We measure our lives in days, our histories in centuries, yet something larger than any empire, older than any species, steers our star like a leaf on an autumn stream. The discovery should dwarf us. Instead, it connects us. Every atom in your body once drifted in the cosmic dark, unclaimed by any sun. Now those atoms have arranged themselves into nerves, into eyes that can look back across space and time, into a mind that can name the flow and wonder what it means. The universe is not outside us. It has folded itself into thought. One day, billions of years hence, the Shapley concentration and the Great Attractor will have merged into a single, colossal supercluster. By then, the expansion of space will have carried all other clusters beyond the horizon. A future astronomer, standing on a cold planet circling the last visible galaxy, will gaze into a sky nearly empty of neighbors and perhaps never guess that the cosmos was once thronged with islands of light. We are lucky. We live while the river still runs, while the galaxies still converse across the void, while the current can be measured and named. So, when night falls, step outside and look south if your sky allows. You will not see the Great Attractor. It hides behind the Milky Way's star clouds. Yet every glance across the cosmos is a glance into a mirror. The same gravity that herds galaxies herds your gaze. The same expansion that stretches space stretches the moment between heartbeats. The same darkness that veils the attractor veils the future. And still we chart the flow, because to chart is to remember that we are part of the current, not outside it. What other hidden attractors wait beyond the curtain of the observable? What larger rivers carry us toward destinations we have not yet words to name? The night keeps its own counsel. But somewhere already, the next chapter is gathering mass. On a quiet October morning in 2017, a telescope high above the cloud line of Maui noticed a speck of light where none had been the night before. At first, the discovery looked routine. A drifting rock, perhaps a comet that had wandered in from the outer dark. But within days, its path refused to bend to the sun's gravity in any ordinary way. It was moving too fast, far too fast, on a track that would carry it back into interstellar space with the same unbroken stride of a traveler who has no intention of staying. For the first time in history, humanity was looking at something that had formed around another star, crossed the gulf between suns, and briefly joined the traffic of our own world. The object was given a Hawaiian name that means scout or messenger, Oumuamua. With that single visitor, the cosmos tilted. The familiar neighborhood of planets suddenly felt like one porch light in an immense city, and something from farther away had stepped into the glow. Until that moment, every asteroid, every comet, every grain of dust we had ever studied had belonged to the same family album as Earth. They coalesced from the same disk of gas and dust that birthed the sun 4.5 billion years ago. Their chemistry is our chemistry. Their stories, however ancient, are part of our origin tale. But Oumuamua was never part of that story. It condensed in a place we will never locate with certainty, around a star whose light we may never isolate in the crowded sky. It was flung out, perhaps by a giant planet's gravity, perhaps by the death throes of its star, sent on a voyage longer than the age of our species. Between its natal fire and our brief glimpse, it drifted through darkness we can scarcely measure, darkness where the sun itself shrinks to a brighter speck among thousands. We saw it only when it was already leaving. By the time our largest telescopes were trained upon it, the object had swept past the sun, climbed above the plane of the planets, and begun its ascent back into the oceanic dark. In the handful of weeks it remained bright enough to detect, astronomers gathered every photon they could. The data were sparse and puzzling. No coma of vapor, no bright tail. It looked nothing like the comets we knew. Instead, its brightness changed by a factor of 10 every 7 hours, suggesting a shape longer than it was wide. Perhaps a flattened shard, tumbling like a thrown baton. Spectroscopy revealed a ruddy surface, the color of cosmic radiation-weathered rock, but told us little of what lay beneath. We never resolved its silhouette. Even at closest approach, it appeared smaller than a few pixels on our most sensitive cameras, a breadcrumb glimpsed from miles away. A year and a half later, another interloper arrived. Comet Borisov streaked in from the direction of the constellation Cassiopeia, trailing a ghostly tail of cyanide and carbon monoxide. This time the telltale signature was obvious. A fuzzy head, a streaming coma, an orbit that hyperbolaed away from the sun. Borisov was everything Oumuamua was not. Where the first visitor had been dry and inert, Borisov bled frozen volatiles into space, sublimating in the warmth of sunlight like any ordinary comet. Its chemistry, measured in the narrow bands of light its gases absorbed, carried fingerprints of a birthplace colder and richer in carbon than our own outer solar system. We watched it split fragments from its nucleus, little snowballs calving in slow motion. Whatever star Borisov once orbited, it must have formed beyond that system's snow line, in a region where ice hung like frost on every grain of dust. The comet's passage gave us a second, richer chapter in a story that had begun with bewilderment. Together, these two messengers rewrote the textbooks. Before their arrival, the existence of interstellar objects was purely theoretical. Models predicted that planetary systems should eject billions of small bodies during their youth, that the space between stars must be thick with these vagabonds. Yet theory offered no promise we would ever see one. The distances are too great, the objects too small, the cosmic spotlight too dim. To detect something a few hundred meters across while it glides past Neptune's orbit is like noticing a single snowflake against the dark flank of a mountain at dusk. That we succeeded twice in 3 years hints at a population far denser than we dared imagine. Every cubic astronomical unit of space may hold fragments of distant Earths, fragments we have never touched or tasted. Discovery itself is a delicate art. The Pan-SDARRS telescope that caught Oumuamua patrols the sky every clear night, photographing the same swaths of stars over and again. Software subtracts one image from the next. Anything that moves or brightens is flagged. Most turn out to be mundane. Slow asteroids circling within the belt between Mars and Jupiter, or distant Kuiper belt objects drifting in cold storage. But a handful of dots refuse to fit. Their motion is too swift, their curvature too steep to close any elliptic around the sun. When 3 or more nights of data align along a hyperbola, astronomers pause. Telescopes larger, farther south, or orbiting above the atmosphere are cabled urgent requests for time. Within hours, a fragile arc of measurements lengthens into a confident trajectory. Sometimes the object is already fading. Sometimes it brightens as it nears the sun. Each new detection is a race against the departure. Trajectory analysis is the closest we come to holding these strangers in our hands. The path of an interstellar object carries the momentum of its entire history. The rotation of its original galaxy, the gravitational kicks of its home system, the gentle nudge of stellar winds, the slow tug of galactic tides. From a handful of points on the sky, computers rewind time, searching for a place where the object might once have been at rest relative to a star. No origin has yet been confirmed. The errors are too large, the possible birth families too numerous. Yet the exercise is not futile. Each attempt maps the rough neighborhoods of the galaxy where rocky planets like ours might form. Each failure reminds us how little we know of ordinary exoplanetary systems. We are like sailors who have found driftwood on a beach and can only guess which continent once shaded the tree. Physical properties are harder still. We measure brightness, not size. If we guess the reflectivity of the surface, we can estimate a diameter, but the range is wide. A shiny shard of metal might be only tens of meters across. A dark lump of carbon only a little larger than a city block. Shape is inferred from the way light fluctuates as the object spins. A simple cigar was the first headline, but a flattened disc or even a shard broken from a larger body fits the data just as well. Density remains a mystery. Without a gravitational tug on a passing spacecraft, we cannot weigh these visitors. They could be porous as frozen smoke or solid as iron. Every interpretation is a silhouette projected onto a cave wall. The absence of a coma around Oumuamua sparked the most controversy. Comets that spend eons beyond the snow lines of their systems should arrive rich in ice. Yet Oumuamua showed no outgassing, no tail, no bright halo of dust. Some researchers suggested it was never a comet, but rather a shard of rock ejected from the inner zone of its system, a fragment of someone else's Earth. Others proposed the ice was there, locked beneath a crust hardened by cosmic rays, able to vent only trace amounts of hydrogen that our instruments could not detect. A bolder idea proposed pressure from sunlight itself, pushing the object like a sail. Such acceleration would require an extraordinary thinness, millimeters thick, lighter than the foil of a party balloon. The suggestion ignited headlines about alien technology. The mundane truth may simply be that we caught Oumuamua too late after its surface had been scorched clean. We will never know. The object is already beyond Saturn's orbit, fading by the month, destined to wander the galaxy until some distant star pulls it into a new gravity well. Comet Borisov offered comfort to traditionalists. Here was an interstellar body that behaved exactly as our own comets do. Its tail streamed across 1,000,000 kilometers. Its gases carried the raw ingredients of distant worlds: carbon, oxygen, nitrogen. We tasted another solar system's chemistry in real time, no spacecraft required. The abundance ratios resembled comets that formed in the cold outer reaches of our own system, suggesting that the recipe for icy planetesimals may be universal. If life ever needed the seeded delivery of organics, the galaxy appears well stocked. Borisov's passage was a gentle confirmation that we are not unique, that the same processes shaping our outer dark have shaped others. Future detections will come faster. The Vera Rubin Observatory, now rising in the Chilean Andes, will image the entire accessible sky every few nights. Its mirrors and sensors will notice objects 10 times fainter than Pan-STARRS can see and motion 10 times slower. Statistical models predict that within a decade we will catalog dozens of interstellar visitors, some perhaps as large as small moons. Each will arrive with its own eccentricities. Some may flash like comets. Others may drift silently, their surfaces baked by 1 billion years of starlight. A few might be shepherded into temporary orbits around Jupiter, captured for centuries before escaping again. One day, humanity may launch a probe fast enough to rendezvous before the object departs. A few kilograms of another star's material, returned to Earth, would speak in isotopes we can measure atom by atom. We would hold a library from a place we will never reach. Until then, we are left with the simple knowledge that the space between stars is not empty. It is threaded with the shattered remains of worlds we will never see, cast outward by gravity's violence, wandering forever. Some fragments may carry the minerals that form rocky planets. Others may ferry frozen gases that seed atmospheres. A few might even harbor the chemical precursors of life. Each passerby is a reminder that the galaxy is older, larger, and more interconnected than any sky of constellations suggests. We live on one quiet shoreline of a cosmic ocean, watching driftwood come and go. When the next visitor arrives, and it will, astronomers will again set aside their planned programs, swing telescopes, and begin the delicate choreography of tracking. Children who today learn to spell the letter O will grow into adults who map the orbits of objects born beneath alien suns. Perhaps one of them will design the engine that overtakes such a traveler, that matches its speed and gently lands. Perhaps another will stand in a clean room years later, holding a capsule no larger than a lunchbox, knowing that every atom inside was forged in a place human eyes have never seen. The thought slows the breath. It places our calendars and quarrels into a hush vaster than any single lifetime. In the meantime, the night sky carries on its ancient rotation. The same stars that guided sailors across oceans still rise and set, but we look at them differently now. We know that some invisible shard may already be coasting through the dark beyond Pluto, inbound, silent, unknown. It will not announce itself. It will not glow until the sun's warmth stirs its ices or its surface catches the first distant glint of our light. When it does, We will greet it with mirrors and spectrometers, with questions we have spent centuries learning to ask. And when it leaves, we will watch it go with gratitude, aware that we have witnessed something no generation before us ever could. A fragment of another star's story, briefly overlapping our own. Somewhere out there, other minds we may never meet are perhaps watching their own interstellar wanderers, measuring trajectories, writing papers, dreaming of oceans unlike any we know. The galaxy is full of messengers, crossing between islands of light, carrying no purpose but motion. We stand on one such island, eyes wide, palms open, listening for the next footfall in the dark. At the very center of our galaxy, 26,000 light-years away, hidden behind curtains of dust so thick that visible light cannot slip through, something stirs. It is not a star, though it outweighs 4 million suns. It is not a planet, though it spins like a silent hurricane in the dark. It is Sagittarius A star, the supermassive black hole that anchors the Milky Way, and it is restless. For decades, we could only guess at its temperament. Radio whispers and infrared glimmers told us a monster lived there, yet the beast seemed drowsed, an immense gravitational mouth with no food to swallow. Then, one night in the late 90s, an infrared telescope caught a spark. In less than an hour, the dim dot at the galaxy's core doubled in brightness, then faded again. A flare, a hiccup of light from a throat that should swallow light forever. We have been watching ever since. Picture the scene. A star the size of the sun drifts too close. It does not fall straight in, few things do. Instead, it skims the edge, caught in a widening gyre of hot gas already circling the hole like an unquiet ocean. Tides rise on the star itself, 1,000-kilometer bulges raised by gravity stronger at its near side than its far. Plasma peels away in ribbons, spiraling inward, accelerating until it brushes a third the speed of light. Collisions shock the gas to 100 million degrees. Magnetic fields, braided and stretched, snap and reconnect, flinging a few lucky electrons into open space at nearly light speed. When those electrons curve, they emit a single, clean note of light, synchrotron radiation. An infrared and X-ray scream that races outward, clears the dust, and reaches our telescopes on Earth. A flare is born. Each act is brief, minutes to hours, yet it carries the energy of a small star burning for centuries. We see them 2, 3, perhaps 10 times a day. They flicker like fireflies against the edge of forever, and each flash is a telegram from the warped clockwork of extreme gravity. The Event Horizon Telescope sharpened the picture. In 2017, its dishes, spread across continents and hemispheres, turned in concert towards Sagittarius A star and gathered the radio light cast by gas on the brink of vanishing. 2 years later, the image arrived. A soft, lopsided ring, brighter on one side where matter hurtles toward us, darker on the other where it recedes. The ring's diameter is as wide and angular size as a grapefruit on the moon seen from Earth, yet it encircles a void no larger than Mercury's orbit. Inside that ring, spacetime folds in on itself so completely that time, from our distant vantage, seems to stop. The image is a still frame, but flares remind us the scene is alive. Still, flares are not simple sparks. Their light curves rise and fall in patterns, some steep, some lazy, each encoding the geometry of the last stable orbit, the spin of the black hole, the viscosity of a fluid we can never touch. By reading these curves like sheet music, astronomers learn the hole's spin is modest, perhaps 20% of its maximum allowed value. That is slow compared with the galaxy-sized engines of quasars, yet it is enough to drag the surrounding spacetime into a whirlpool 4 times wider than the hole itself. Within that dragged frame, infalling matter finds extra resistance. Some is flung outward, some slips inward, and the balance decides whether a flare ignites or the flow merely sulks in infrared dusk. Between outbursts, the accretion disk is so tenuous that a matchbox of its gas would weigh less than a snowflake. Yet spread across tens of millions of kilometers, that trace plasma glows like a dying coal. Watch long enough and you will see it surge, brighten, dim, surge again. Heartbeat of a creature whose pulse is governed not by biology but by magneto-hydrodynamics and the cruelty of tidal forces. Compare this with bigger cousins. The black hole at the core of M87 outweighs Sagittarius A star by 1,500 times. Its dinner is a banquet, and its flares are tsunamis of light visible across intergalactic space. Our black hole is on a starvation diet, yet it still manages to stamp its foot. In 2019, an X-ray flare 20 times brighter than anything previously recorded erupted, lasting only a few minutes. Had any planets circled within a few light days of the center, their upper atmospheres would have been stripped away like paint under a blowtorch. Earth, orbiting in the peaceful suburbs, felt nothing, but the flash crossed the galaxy unimpeded, a reminder that even quiet giants can roar. We are learning to listen. Telescopes now orbit beyond the blurring veil of our atmosphere. The Chandra X-ray Observatory, new star with its lobster-eye mirrors, the upcoming XRISM mission that will split flare spectra into 1,000 colors. On the ground, the Very Large Telescope's gravity instrument interferes 4 giant mirrors to create a virtual eye 8 meters across, sharp enough to watch star clusters whirl around the hole in real time. Within the decade, the next generation Event Horizon Telescope may record movies, not snapshots, frames separated by seconds, showing hot spots of plasma as they spiral 2 full turns before slipping past the event horizon. We will watch the last photon surface, the ghostly boundary where light itself can still orbit but never escape, and we will see it shimmer. What we do not yet know is how flares begin. Perhaps magnetic islands rise from the disk like solar prominences, twist and snap. Perhaps clumps of cool gas rain inward, shocking the hotter flow into incandescence. Or perhaps the black hole's own spin couples to the plasma through frame-dragging, winding field lines into tight coils that lash out like cosmic whips. Each hypothesis leaves fingerprints in polarized light, and new detectors are being built to read them. There is also the quiet promise of neutrinos. If protons as well as electrons are accelerated in flares, they will collide with ambient photons and produce ghost particles that carry away a fraction of the energy. A cubic kilometer of Antarctic ice, instrumented by the IceCube array, waits for these messengers. A single high-energy neutrino traced back to the galactic center would confirm that black holes can act as cosmic particle accelerators, a possibility once reserved for supernovae alone. And what of time? Aboard a spacecraft hovering just outside the last stable orbit, you would see the universe flash forward. Stars would streak into arcs, the cosmic microwave background would blue shift into visible light, and the 10-minute flare we measure on Earth would race past in a handful of seconds. You could watch civilizations rise and fall between heartbeats, yet to the distant astronomer your own clock would seem frozen. Flares thus become hourglasses where gravity itself measures the passage of eras. We map these rhythms because we are tethered to them. Every star in the Milky Way, including our Sun, migrates in the gravitational well carved by Sagittarius A star. Our orbit is a calm circle 2/3 of the way out, but it is still a motion within the empire of the black hole. We are not falling in, yet we are subjects of its rule, our velocities subtly stirred by its mass. In that sense, flares are the drumbeats of a sovereign whose throne room is wider than the solar system, but whose decrees are written in Einstein's equations. So we keep vigil. Night after night, infrared cameras chill their detectors to near absolute zero, radio dishes tilt in mechanical prayer, and computers sift petabytes of data for the telltale spike. Each flare is a postcard from a place where density becomes infinite and volume vanishes. Each is also a mirror. In their brief blaze, we see the limits of our understanding, the point where our best theories fray into question marks. One day, perhaps, a flare will arrive unlike any before. Brighter, longer, laced with the spectral signature of iron atoms stretched and compressed in ways only possible near the event horizon. On that day, we will know that matter has slipped past the final gateway, carrying with it the magnetic memories of everything it once was. The light will not escape, but its last exhalation will reach us, a whispered confession before the curtain falls. Until then, the heart of the galaxy remains both familiar and foreign, a reminder that stillness is often an illusion crafted by distance. Up close, the monster is restless, and its every tremor reaches across millennia to touch the quiet waters of our telescopes. We study these motions not to conquer but to comprehend, to feel the tug of something larger than ourselves and to sense, if only faintly, the deeper rhythms in which our own lives are set. Out there beyond the dust, time and space are singing. We are only beginning to hear the song. Light is a time traveler. Crossing the gulf between stars, it carries yesterday's news to today's eyes. But there is one glow so ancient that, when we see it, we are looking all the way back to the morning of time itself, a hush of radiation released when the universe was a mere 380,000 years old. We call it the cosmic microwave background, the afterglow of birth. It arrives from every direction, a gentle whisper of heat barely warmer than absolute zero, and yet within its hush lie patterns, tiny ripples of temperature painted across the sky like brushstrokes on a dark canvas. For decades we studied those ripples, measuring their spacing, their brightness, their symmetry, convinced they would confirm the elegant story we had written about inflation, the split-second burst that swelled the infant cosmos smooth and flat. And mostly they did. But hidden among the thousands of warm and cool dapples, one patch refuses to behave. It is colder than theory allows, larger than theory allows, and oddly empty of galaxies. In the literature, it is simply the cold spot. Say the name aloud and even seasoned cosmologists pause as though reluctant to disturb something that may be listening. Imagine the sky as a vast globe of black glass. Every star you have ever seen is a grain of sand glued to the inner surface. The space between is the vacuum we once thought featureless. Now picture a region the width of your outstretched hand held at arm's length, a zone 20 degrees across, where the glass has been chilled by an extra 300 millionths of a degree. Such a sliver seems laughably small, yet in the arithmetic of the early universe it is a canyon. Random fluctuations should not carve canyons this wide. Inflation, our great smoothing iron, was supposed to erase them. When the first full-sky maps arrived from the WMAP satellite in 2003, the spot sat there like a missing puzzle piece, pale and conspicuous. Statisticians ran their algorithms, asked the data how often such a void might arise by chance in a universe obeying the standard rules. The reply came back, 1 in 200, perhaps 1 in 50, depending on how you frame the question. Not impossible, merely unlikely, an uncomfortable gray zone where science must decide whether to shrug or to keep digging. The digging has occupied 20 years. New instruments, Planck, ACT, SPT, mapped the microwave sky with ever finer pencils, confirming again and again that the cold spot is real, not some instrumental ghost. Meanwhile, telescopes counting galaxies across the same patch found an underdensity. A vast bubble containing roughly 20% fewer galaxies than the cosmic average, a desert stitched into the cosmic web. One might think the two observations easily married: fewer galaxies, less gravitational clumping, lower integrated photon temperature. But the numbers still refuse to align. Even when we account for the missing galaxies, the radiation remains too cold, too wide, too smooth. Something else is at work, something our textbooks did not foresee. So we are led to question the story itself. Inflation is a graceful idea. A fraction of a second after the Big Bang, a repulsive energy field stretched space faster than light, ironing out curves and diluting contaminants until only the faintest wrinkles remained. Stop the expansion history at any random moment, and inflation predicts a very specific statistical fingerprint: temperature variations of a particular size and distribution. The cold spot is too large to fit that fingerprint, like a thumbprint smudged across an otherwise delicate line. Either our sample of sky is a fluke, one of those rare corners where chance conspired to look unlikely, or the fingerprint is incomplete, a first crude sketch of a richer pattern. Alternative explanations have begun to bloom. Perhaps a topological defect, a remnant crack from a symmetry-breaking transition, wandered across our line of sight, its intense gravitational field redshifting the light that passed through it. Or maybe two vast bubbles of space were caught in the act of nucleating during inflation, colliding after the expansion had ended, leaving a bruise. Some theorists invoke a second, shorter burst of inflation, an extra heartbeat, able to generate larger, colder patches. Others step outside the hot Big Bang altogether, proposing that the universe emerged from a bouncing phase, a slow contraction followed by expansion, and the cold spot is a scar left by quantum fluctuations that survive the bounce. Each scenario carries its own subtle signatures, predictions waiting for sharper eyes to test them. Those eyes are being built. On a high plateau in the Atacama Desert, the Simons Observatory is taking shape. A cluster of microwave telescopes whose detectors number in the tens of thousands, cooled to a fraction of a degree above absolute zero, listening for the faintest tremor in the cosmic hush. Within the decade, the Lightbird satellite will orbit the Earth-Sun L2 point, sweeping the entire sky again and again, mapping polarization patterns that carry twice the information of temperature alone. If the cold spot is a window, these machines will press our faces closer to the glass, searching for the telltale swirl of primordial gravitational waves, the soft echo of bubble collisions, or the subtle alignment of polarization angles that might betray a defect in space-time. Each new pixel is a fresh lottery ticket in the gamble of discovery. Yet even before the data arrive, the spot has already altered our sense of scale. We once pictured cosmic anomalies as microscopic, quantum jitters blown large by expansion. Now we must imagine that some features could stretch hundreds of millions of light-years across, grand enough to dwarf clusters of galaxies, yet subtle enough to hide within a temperature difference smaller than the warmth of your breath against the night sky. The universe, it seems, is willing to write poems in letters larger than kingdoms, visible only to those who learn to feel the cold between the stars. There is, too, a quieter implication. If the cold spot is a signpost to new physics, then the smoothness we once celebrated, the gorgeous uniformity that allowed galaxies, chemistry, life to emerge, may itself be an interlude. Beyond the horizon, inflation might still be happening, bubbling off pocket universes whose physical constants differ from ours, each too distant ever to signal. We would live inside one calm eddy on an ocean of eternal expansion, our laws of nature a local dialect in a much grander conversation. The thought is humbling, yet strangely consoling. The same sky that chills us with remoteness also assures us that remoteness is not emptiness, but room for endless beginnings. So when next you step outside on a clear, moonless night, let your eyes adjust until the darkness pools like ink. Above you, the ancient firelight of the cosmic microwave background is falling, a gentle rain of photons that outnumbers every star you see. Somewhere in that hush lies the cold spot, drifting across the constellations like a shadow without a source, reminding us that even the earliest light carries secrets we have not yet learned to read. We are the first creatures we know of who can look back and wonder. Others may follow, armed with sharper senses, new languages, longer patience. Perhaps they will map the spot and find it ordinary, one island in an archipelago of anomalies. Or perhaps they will discover that the chill we felt was the first breath of a larger wind blowing through corridors of space-time we have not yet imagined. Either way, the echo will still be traveling, a ripple on the surface of eternity, waiting for minds ready to listen. Imagine a world where the shoreline is not sand but ice, where the waves do not crash in salt water but rise and fall in slow-motion silence, moved not by tides but by the pull of gravity from a distant ringed giant. This is Titan, Saturn's largest moon, and it is home to something no other world in our solar system can claim, standing liquid on its surface. Not water, but something far stranger. Here, in the cold twilight of the outer solar system, methane and ethane fall like rain, gather into rivers, and settle into vast, placid lakes. Some of these lakes are larger than Earth's Black Sea. Others are no more than shallow ponds, hidden in the folds of a landscape carved by wind and chemistry rather than by time. If you could stand on Titan's surface, you would not feel the kiss of sunlight as we do on Earth. The sun from here is nearly 1 billion miles away, shrunk to a bright star in a sky forever tinted orange by a thick, hazy atmosphere. The air itself is denser than Earth's, and every breath you took, if you dared, would carry the scent of petroleum and damp stone. Gravity is gentle here. A leap would feel like slow flight, but the cold would kill you in seconds. At -180 degrees Celsius, water is rock hard, and the only things that flow are the hydrocarbons, methane, ethane, propane. Substances we think of as gas or fuel, but here they play the role of water. It is easy to think of these lakes as exotic curiosities, distant and irrelevant to us. But they are more than that. They are a second kind of ocean, a mirror to our own, shaped by the same physics but built from different materials. On Earth, water evaporates, rises, condenses, and falls again. On Titan, the cycle is the same, but the actors have changed. Methane evaporates under the faint sun, climbs into the sky, forms clouds and drifts. When it falls, it does not roar like a monsoon. It drops in a soft, slow drizzle, the droplets large and lazy, splashing into lakes that have waited centuries for the storm. Over thousands of years, the lakes shift. Some expand. Others evaporate into plains of cracked mud, not made of dirt but of organic haze that has rained from the sky for eons. This is weather, but not as we know it. When the Cassini spacecraft arrived at Saturn in 2004, it carried with it a small probe named Huygens, built by the European Space Agency. On a cold January morning in 2005, Huygens detached and drifted toward Titan. It parachuted through the thick atmosphere for 2.5 hours, snapping images of river channels that looked like they belonged in the Amazon. It landed not with a splash but with a thud on a surface that was neither wet nor dry, something in between. The probe's sensors detected methane vapor evaporating from the ground. It had landed in what once might have been a floodplain. The images it sent back showed rounded pebbles, not of rock but of water ice polished by the flow of liquid methane. For the first time, we saw a landscape shaped not by water but by chemistry. Cassini continued to orbit Saturn for 13 years, swinging past Titan more than 100 times. With each pass, its radar pierced the haze and mapped the surface. What emerged was a world of contradictions. Near the North Pole, lakes cluster like droplets on a spider's web. Some are deep enough to drown a skyscraper. Others are shallow, their bottoms visible in radar shadows. One lake, named Kraken Mare, is larger than the Caspian Sea. Its waves, if they exist, are only millimeters high, slowed by the thick air and low gravity. But they are waves nonetheless, stirred by wind across a sea of liquid natural gas. We once thought Titan's lakes were smooth and stagnant, but Cassini showed us otherwise. In spring, when sunlight returns to the north, clouds form. Methane storms sweep across the lakes. The liquid level rises and falls like the tides of a distant ocean. Some lakes have narrow inlets and outlets, suggesting rivers feed them from below. Others are closed basins, slowly evaporating, leaving behind bathtub rings of organic residue. These residues are not life, but they are the kind of chemistry that on Earth led to life. A planetary scientist once said that Titan is not a world where life exists, but where the ingredients are being mixed in a bowl left out on the counter. Time will tell what rises. The question then is not absurd. Could something swim in these alien seas? Not fish as we know them. There is no oxygen here, no sugars, no proteins. But life is not a single recipe. It is a process. It gathers energy, replicates, adapts. On Titan, energy could come from acetylene reacting with hydrogen, releasing just enough heat to power slow, cold metabolisms. Cell membranes might be made of organic azotosomes, flexible in the chill. Reproduction would be unrecognizable, perhaps based on hydrocarbon chains rather than DNA. Such life would be small, sparse, slow. A day on Titan lasts nearly 16 Earth days. A season, 7 Earth years. Evolution would crawl, but it would have time. Titan is ancient. Its surface has been stable for billions of years, far longer than Earth's continents. If the first spark of life ever took hold here, it may still linger in the mud along the shores of these quiet lakes. We are not left to wonder much longer. In 2027, NASA will launch Dragonfly, a rotorcraft lander the size of a small car, powered by a nuclear battery. It will arrive in 2034, drifting through Titan's orange sky, hopping from site to site. It will land first in the dunes near the equator, where organic sand grains gather like snow. Then it will fly, yes, fly, tens of miles in a single hop. Something impossible on Earth but effortless in Titan's thick air and low gravity. Over the course of nearly 3 Earth years, Dragonfly will make its way toward Selk Crater, where impact once melted water ice and created conditions that, for a brief moment, might have allowed Earth-like chemistry to mingle with Titan's hydrocarbons. There, it will search for the building blocks of life, or perhaps for life itself, frozen in slow motion. There is something humbling in these lakes of methane. They remind us that the universe does not need Earth's recipe to create complexity. Water is not the only solvent. Carbon is not the only scaffold. Life, if it exists elsewhere, may not breathe or swim or fly as we do. It may simply endure, hidden beneath a sky we will never see with our own eyes. And yet, we are going. Across a billion miles of silence, we are sending a machine with spinning rotors and gentle legs to touch the surface of a world where rain falls in slow motion and lakes wait patiently for visitors. Perhaps one day we will stand there, encased in heated suits, watching the methane mist drift across a lake so still it reflects the stars like polished glass. We will kneel, scoop the liquid into gloved hands, and wonder what strange futures might be stirring in its depths. Until then, Titan keeps its secrets beneath a sky of amber haze, a world where the seas are not of water but of memory, of what the cosmos can create when it is given nothing but time, chemistry, and the quiet cold. On the night of August 15, 1977, a narrow column of radio energy rose from the constellation Sagittarius, crossed the black waters of space, and for 72 seconds brushed the outstretched wire of a single antenna in rural Ohio. The instrument did not notice, but a young astronomer named Jerry Amon, reviewing the computer printout the next afternoon, noticed. He circled the unexpected pulse of numbers and letters, leaned back, and wrote one word in the margin. "Wow, In those 3 letters, he captured both the thrill and the ache of every search for company among the stars. A signal had arrived, or seemed to. It arrived once and never again. To understand why this moment still lingers in the corridors of astronomy, picture the radio sky as an ocean of whispers. Galaxies murmur, pulsars click like distant lighthouses, hydrogen clouds hum their primordial song. Most of these voices are broad, diffuse, untuned. Intelligence, if it ever broadcasts, is expected to sound different, sharp, deliberate, narrow as a knitting needle in the dark. The WOW pulse was needle-thin. Its frequency, 1,620 MHz, sits in a band protected by international agreement. Terrestrial transmitters are forbidden to stray there, lest they swamp the quiet line where hydrogen, the commonest element, sings to itself across space. An emitter tuned to that channel would be either careless or considerate, either reckless with its own privacy, or deliberately clearing a path so others might hear. The antenna that caught the burst was no gleaming dish beloved of television. It was a pair of flat, tiltable metal mirrors flanking a central feed, looking like an abandoned railway bridge set on its side. Big Ear, it was called, and it was designed to sweep the sky slowly, passively, day after day, mapping the faint radio continents of the universe. Each patch of sky received scrutiny for about 72 seconds as Earth turned. A celestial source stationary relative to the stars would rise, brighten, and fade in exact mimicry of the telescope's beam. The WOW. Intensity traced that rise and fall, a symmetrical bell curve in time, exactly as a distant point source should. Whatever it was, it behaved as though it belonged to the sky, not to the noisy ground. Yet when astronomers swung other ears toward Sagittarius, they heard only the usual hush. Hours, days, decades followed, nothing repeated. A single, perfect syllable had been spoken into the dark. The cosmos, if it heard, offered no echo. The search for extraterrestrial intelligence lives on such silences. SETI observers stack millions of narrow channels, listen for years, and still treasure the rarest coin of their realm. A signal that looks like technology rather than chemistry. They ask for persistence, for drift, for modulation. A carrier wave that wiggles, that carries information, would betray a mind behind the mic. The WOW burst carried no obvious message, no sidebands, no pulse code. It was a pure tone, bright as a flashlight switched on and off. Some researchers argued it might still be intelligence. A beacon, a lighthouse sweeping its beam across the plane of the galaxy, briefly touching us. Others preferred the universe's ordinary miracles. An unknown comet, perhaps, whose halo of ions glowed in just the right way, or a one-in-a-million reflection from a piece of human debris spinning like a mirror through the void. In 2017, a professor proposed that comets rich in hydrogen-bearing ice, passing unseen through the beam, might release clouds that mace, that amplify a faint whisper into a sudden shout. When the predicted positions of 2 such comets were wound back to 1977, they overlapped the WOW patch of sky. Excitement rose, then ebbed. The calculated signal strength fell orders of magnitude short, and the comets themselves were later found not to have been in the beam at all. The explanation dissolved, leaving the mystery intact. Still, the pulse did what all good mysteries do. It deepened the hunt. After Big Ear was dismantled and its mirrors left to gather ivy, newer telescopes turned digital ears toward the stars. The Very Large Array in New Mexico, famous for imaging galaxies, once spent a night in service to SETI, listening to the WOW, coordinates with a sensitivity tenfold finer. Silence. The Arecibo dish, nestled in a Puerto Rican valley, scanned the same region while its massive platform moved like a sleepy eye. Nothing. In 2020, the 500-meter dish in China joined the vigil, its bowl of aluminum panels cupped toward Sagittarius for months. The data grew into terabytes, then petabytes, a library of absence. Yet absence is not failure. Each quiet night tightens the cage of possibilities. Statistically, we can now say that if the wow event were repeated regularly, say, once a year or once a decade, we would have heard it again. Its failure to return pushes it toward the realm of the singular, a flare that may never repeat within the lifetime of our species. Perhaps it was a military satellite tilting its antenna, leaking a stray harmonic before burning up in the atmosphere. Perhaps it was a momentary marriage of two ordinary signals, multiplying in the air to produce a ghost tone that lived for 1 minute and died. Or perhaps it was the real thing, a civilization's hail, offered once on the off chance that someone, somewhere, would be listening at the right instant. The galaxy is old enough for civilizations to rise and fall like civilizations do. Their monuments may outlive their attention spans. A single beacon, sweeping the galactic plane every million years, would still flash upon thousands of worlds. We might have been one. To live with such possibility is to accept a certain vertigo. Science, for all its instruments, still balances on the raw experience of a lone human being, coffee cooling at his elbow, marking a sheet of paper in red pen. Jerry Amon never claimed the signal was aliens. He simply refused to dismiss it, and in so doing gave the rest of us permission to wonder. Every year, on August 15th, a few amateur astronomers still aim homemade dishes toward the galactic center, quieting their phones, listening through headphones as if leaning against the sky's own chest to hear a heartbeat. They know the odds, they listen anyway. The search itself has become a kind of civilization, small but tenacious. Projects with gentle names, Breakthrough Listen, Project Phoenix, the Allen Telescope Array, scan star after star, searching for the narrow lines that nature never draws. Algorithms sift the torrent faster than thought, flagging tones that hover, that drift, that whisper in patterns a human ear might miss. When a candidate appears, telescopes thousands of kilometers apart swivel in choreographed haste, comparing notes to rule out earthly interference. Most signals die at this hurdle, dissolving into airport radars, into orbiting clocks, into the secret dances of spy satellites. A few survive long enough to be written up, debated, then gently laid to rest in the archives of almost. Still, the process refines itself. Each false positive teaches the machines to be more discerning, more patient. Meanwhile, the tally of known planets climbs. 5,000 confirmed, tens of thousands suspected, many of them small, rocky, temperate. Around red dwarfs where years last weeks, around suns older than our own, the possibilities for life accumulate like dew. If intelligence is rare, it is no longer unthinkable. If it broadcasts even once, we may be ready. And so the night sky above us has become a quiet conversation we are learning to overhear. Radio telescopes rise like flowers in deserts, on high plateaus, in craters of extinct volcanoes, places where the air is thin and human voices fade. They listen not with the urgency of a telegram, but with the patience of trees. Their data travel fiber optic routes beneath oceans, linking continents into one great ear. Children in classrooms adopt individual stars, monitoring the faint static for anomalies, their teachers guiding them through spreadsheets of silence. Some of these children will grow up to be the first humans who know, with certainty, that we are not alone. Others will inherit only deeper questions. Both fates are honorable. In the end, the wow signal remains what it was, a single, bright syllable in a language we do not speak. It may have been an accident of physics, or a greeting, or something we have not yet imagined. Its importance lies not in the answer it failed to give, but in the question it forced us to keep asking. To listen is to admit that the universe is larger than our stories, yet still worth eavesdropping upon. If no voice ever answers, we will have learned at least that silence itself can be fertile, that wonder can live inside a string of numbers, that a momentary pulse, captured, circled, cherished, can keep an entire species looking up. Somewhere tonight, as Earth turns its dark side outward, the same strip of sky that once flared in Ohio drifts overhead again. The hydrogen line waits, pristine, uncluttered. A new telescope or an old one newly repaired tilts its face. Inside a control room, a graduate student yawns, checks the clock, refreshes the plot. The line is quiet for now. Outside, the Milky Way arches like a frozen wave, and beneath it the patient instruments listen, not for certainty, but for the possibility of company. When sunset has slipped behind the farthest ridge and the sky has grown truly dark, the planets we know appear as delicate lamps. Yet, beyond the reach of those familiar wanderers, farther than Neptune's pale sapphire, the sun's realm is not finished. Something still circles, immense and unseen, shaping paths we have only begun to notice. The first hints arrived as tiny chalk marks on blackboard skies. Astronomers mapping the hinterlands of the solar system kept finding small ice worlds whose oval orbits swung out in wary synchrony. Individually, each object was a modest curio. Together, they told a different story, their long axes aligned like spokes of a wheel, as if a hidden hub were keeping order. Random gravity could not easily explain such poise. A concentrated hand seemed required, something heavier than Earth, perhaps 10 times heavier, steering invisibly from the shadows. Imagine a beach at night. Footprints appear, always the same distance from the waterline, always pointing the same way. You never see the visitor, yet the pattern insists on a walker. So it is with these scattered crumbs of rock and frost. Their footprints, written in orbital stone, suggest a planet we have never photographed. The provisional name is simple, Planet 9, yet the implications ripple outward like rings on dark water. To grasp its possible nature, begin with distance. If Planet 9 exists, the sun appears from its vantage not as a blinding disk, but as a hard pearl barely brighter than the full moon on Earth. Sunlight, already frail at Neptune, dwindles there to 1,000th of its earthly strength. Temperatures hover near absolute zero, slow enough to hush every molecule into near immobility. Such a world would not wear the bright cloaks of cloud and ice we admire on Jupiter or Saturn. It would be a coal-black sphere wrapped in frozen gases that only slumber, never evaporate into clouds. From Earth, it would glow not by light of its own, but by the faintest reflection, like seeing a torch beam bounce off a marble from 10 kilometers away. Size, however, is another matter. Models that reproduce the clustered orbits call for a body whose mass outweighs Earth by 5 to 10 times. That heft places it in a strange category. Too massive to be a mere shard of ice and stone, too small to ignite even the dimmest nuclear fire. It would roam the borderland between the giant planets we know and the failed stars we call brown dwarfs. Perhaps it carries a tenuous atmosphere of hydrogen and helium, exhaled in youth and now frozen against its flank. Perhaps it hosts moons, dim as snowballs, locked in slow, stately dances months long. All this lies within the realm of possibility, for the unseen can be painted in many colors until a telescope finally gathers its photons. How then do astronomers hunt something whose only signature is a ghostly gravitational brushstroke? The strategy is patient and indirect. First, they widen the net, discovering more of the small worlds whose orbits betray the hidden hand. Each new traveler tightens the statistical noose, narrowing the corridor through which Planet 9 might glide. Second, they rewind the clock. Computers become miniature solar systems, integrating the slow ballet of giants forward and backward across hundreds of millions of years. Only a narrow range of masses, paths, and tilts keeps the fragile choreography intact. Allow the unseen planet too small a mass, and the alignment unravels. Push it too close, and its gravity would have perturbed the known giants in ways we do not observe. The simulations speak softly but insistently. If the planet is there, it now lingers somewhere along a broad arc of sky, perhaps 600 times Earth's distance from the Sun, in a patch of stars belonging to the constellations Orion, Taurus, or Cetus. With these celestial boundaries penciled in, the true night work begins. Telescopes, their mirrors wide as truck tires, sweep the suspect region, taking long exposures that stack minutes into hours. A distant planet would crawl across the starfield so slowly that it hides beneath the very motion it is meant to betray. Software subtracts one epoch from another, searching for a speck that drifts like a firefly amid fixed stars. So far, that speck has not emerged. Yet absence is not proof of non-existence. It merely narrows the corridor again. The Milky Way is thick with glittering distractions, and Planet 9, if coal-dark, reflects so little sunlight that it hovers near the threshold of what even the largest eyes on Earth can see. There is another, subtler clue. The Cassini spacecraft, orbiting Saturn for 13 years, felt minute tugs from everything in the solar system. Precise radio ranging allowed navigators to calculate its position within meters across 1 billion kilometers. When astronomers included a hypothetical Planet 9 in their gravitational ledger, Saturn's calculated orbit shifted by a few hundred meters, tiny, but tantalizingly close to the margin of what Cassini sensed. The signal is ambiguous, woven into the weave of other planetary masses. Still, it whispers in the same key as the Kuiper belt clustering, a harmonic from a different octave of the same dark chord. What if, after all this patient arithmetic, the planet proves a chimera? Astronomers keep that question alive because science is a conversation, not a verdict. Some propose that the clustering might instead record the memory of a long-lost open cluster, the Sun's siblings from its birth. Others wonder whether a small, primordial black hole could have wandered into the solar system, ghosting among the icy detritus. Such a wanderer would weigh similarly to the predicted planet, yet be no larger than a grapefruit, utterly black and impossible to see by reflected light. The notion sounds outlandish until one recalls that most of the universe's matter is dark, and that our neighborhood is older and stranger than childhood textbooks imply. Whether Planet 9 exists or evaporates into footnotes, the very act of searching rearranges our understanding. Planetary formation theory, once tidy, now admits that giants can be tossed outward like coins flipped across a table. Computer models show that, when the young solar system was still a swirl of gas and dust, Jupiter and Saturn's shifting tides could have flung a nascent world beyond the realm of the known. Out in that chill exile, the planet would have grown slowly, accreting frost and gas, until its gravity carved the distant frontier we now read like a fossil record. Thus, the architecture of the solar system may be more cathedral than cottage, with cloisters we had never noticed. The quest also reframes our sense of scale. If tens of thousands of miniature icy worlds can be discovered in a region once thought empty, how many more dark cathedrals of stone and ice might circle other stars? Each new detection stretches the imagination, nudging us to see planetary systems not as neat nests of 8 or 9 siblings, but as sprawling clans whose members wander vast, dim halls. In that light, Planet 9 is less an oddity than a missing keystone. Its presence would restore symmetry. Its absence would oblige us to invent new physics of clustering, new histories of migration. Meanwhile, the nights continue, and the telescopes open their silver petals to starlight. Graduate students huddle in warm control rooms, sipping tea while algorithms sift petabytes of pixels. Somewhere, a speck may already lie hidden in last season's data, waiting for sharper eyes or a cleverer line of code. Discovery in astronomy is often like this. Years of quiet accumulation, then a single frame that refuses to subtract away, a pixel that insists on drifting. When, if that moment arrives, the world's morning headlines will speak of a new planet. Astronomers will smile quietly, knowing the true discovery began years earlier, in graphs of clustered orbits and in lines of code that no camera flash will ever record. Until then, the outer dark remains an open question, a pause between movements in the solar system's long symphony. We may find Planet 9, or we may find something stranger still. Perhaps several smaller worlds whose combined mass mimics a single giant. Perhaps nothing, forcing us to rethink how orbits remember ancient music. Either path leads onward, because uncertainty is not a failure but a doorway. Each tightened limit, each newfound shard of ice, writes another sentence in the living manuscript we travel within. Stand beneath the stars tonight and consider this. Every pinpoint of light you see obeys gravity's quiet grammar, and somewhere beyond the reach of your gaze, a world larger than Earth may be gliding in centuries-long silence, tugging faintly at the frost-bright nomads we have only begun to catalog. Whether that world ever steps into the light, its story has already altered us, loosening the seams of certainty, reminding us that even close to home, the cosmos reserves its share of shadows. And so, with questions in our pockets and maps half drawn, we edge forward, ready for the next layer of distance, ready for whatever else waits in the hush beyond Neptune.